My name is Murat Keceli. I'm an assistant computational scientist in ALCF and computational science division. I have dual role in data science and the CPS division. Just a year ago, I have been attending these workshops as a user. This is the first time I'm going to talk. And this is the first time I'm going to talk about containers because I actually didn't know anything about containers just a year ago. And I find it really fascinating that all the developments related to HPC containers are evolving very fast, and I'm glad to be part of it. And I hope you will also enjoy using containers on HPC environment from now at some point. So here is just a quick survey to understand how many of our users have already experienced with different virtualization, containerization tools. So these tools are actually quite new, except the virtual machines, which have been around for more than 10 years. But Docker containers, shifters, Singularity, these are all new concepts, relatively new concepts. So it is quite normal that you may not have any experience. While answering this poll, there is another survey that is recommended to be completed about the workshop, but this is just an optional survey just about the containers. I will be glad if you can just answer if you have any experience with these different technologies. It's just yes or no type survey. So far I have seen that we have already 10 users who have been using Singularity and Shifter. So this is actually more than I was expecting. And I should put a disclaimer here that this talk is more about recruiting people to use containers. If you have been already using containers, the second half of the talk might be useful for you, but the rest is just sort of introduction to containers. So, okay, what I am talking about. Containers and virtualizations are basically some tools, productivity tools that helps us to run an app in an application in an isolated environment. So you have a software stack that has lots of dependencies, and you want to run it in an isolated fashion on top of another environment. So this is what virtual machines and containers are doing. So virtual machines are, as I mentioned, an older concept. In these ones, what you are doing is you are running an operating system on top of another operating system. So this was used especially when people were using Linux, but they want to use, for example, Office tools, and they want to run Windows on top of Linux. So this is a tool, virtual machines like VirtualBox or VMware is a tool that people running Linux on top of Windows or Windows on top of Linux are using. The relatively new concept, containers, is what is called as operating system level virtualization. They are at higher level. You are not running a full operating system on top of another one. You just use the kernel of the host operating system. And this is generally just the Linux kernel, because Linux kernel has the capabilities like namespaces, C groups, that allows you to run this type of containerization. Both of them requires an image, but containers can also use a recipe file, which makes life much useful. So I will get more into this later. So why do we need containers? So if you have been trying to port your application to Theta and you have been struggling to, then containers might be very helpful for you. If you are getting constant errors depending on your library dependencies, the versions that you are using, containers can be really helpful. So what are the advantages of the containers? First is, as I mentioned, portability, because you can use, ideally, the same image on your laptop, on your local cluster, and on the supercomputing environment. I will mention there are some catches here, but in general, you can use the same image everywhere. And you don't need to ask system admins to install a specific application for you. You can do everything by yourself and use it in any places and pass it to another person, and he can use the same thing too. Another thing is reproducibility. So, reproducible science is important. And actually, reproducible science is a misnomer because science should be reproducible. It is not science if it is not reproducible. And this is very important in applied domain. When you are doing an experiment, you have to make sure that some other person repeating your experiment does the same. And in computational domain, it should be much simpler, but unfortunately, this is not very much used in many different scientific domains. So people publish their codes, publish their results on their codes, but another person cannot use the same code and get the same results. So containers allow you to run all your application, all your data put into a single image and distribute it, and any people using the same image should get the same result. So this is very helpful in terms of reproducibility. And there are some journals asking specifically from computational people to provide either container images or full software stack so that they can prove their reproducibility. And it allows you faster development because you don't need to install every time you make a change in the code in different machines. So this is similar to what you get from portability, but it also improves your development time. Another way of seeing this is when you try to install something on Theta, you have to do it on the login node. You compile it on the login node, and it can be slow. But here, you can build your image on your laptop, and then you just copy your image to Theta. So this can improve your productivity in that level as well. So is it a silver bullet for all these problems? Unfortunately, no, because there are many cases that it may not work, and it may not be the best solution. So this is an XKCD cartoon, just another one that shows a very actually meaningful critique on containers. So here he is saying that, well, Docker is being used for everything, and the other one is explaining a story here. And the basic message from this story is that he wants to run an app side by side on a tablet, but he needs to write a code for this because the tablet OS does not allow it. At the end, his solution was just to glue two cell phones and run these two apps like this. So this is basically a critique on containers that you are not using your resources in the best fashion. So you are basically hacking a solution into your environment. So some computer scientists are not very happy about containers because they feel like we are not using the resources very effectively. But we know that this is, I like this quote a lot, this is also referred to as parallel computing paradox. So the average time required to implement an application is equivalent to half-life of the HPC environment that you are working on. So we are racing against time. So we may not get the best solution, but we may get a working solution for our purposes. So going back to, so this was basically trying to convince you about the usefulness of containers. Now let's go back to these two different technologies, virtual machines and containers. So as I mentioned, you run a full operating system on top of a host operating system in a virtual machine. So these are two virtual machines running on a server. And on a container, now we don't need to have a guest OS here. We are basically, our applications are using the kernel of the, this should be a Linux host, the Linux kernel here. And then you can run two containers on the same server. And this type of, the main difference between virtual machines and containers is one is using guest operating system and the other is not. And this is basically causing a significant overhead for this one because you need to boot the guest operating system, while the other one is much faster and very lightweight. So therefore, container solutions become more popular. And especially Docker containers, which actually started in 2013, which is an extension of Linux containers that came alive in 2008 or sometime earlier. And it was a very good solution for enterprise because what they can do is they can run many containers on a single server. For example, many different web servers just running on a single server. So this it's very meaningful for enterprise, for different applications, but it's not perfect for HPC environment. In HPC environment, actually, these logos is very meaningful. You see that in Docker Lego, you see many containers on top of it. here, an HPC environment, you basically your interest is only running one container on top of your server, because you want to maximize your performance. You don't want two different containers to share the same resources. So the use case is different. So to answer that use case, there have been different developments recently. Shifter from NERSC and some contribution from, it's mainly developed by NERSC, and I guess Cray has some contribution to it. Charlie Cloud is another one from Los Alamos National Lab, and Singularity from Livermore Berkeley National Lab. This one actually had much more gained traction compared to other ones, and it already become a company. But they are still keeping the sources open, and they are still committed to the HPC environments, HPC centers. So let's look at the comparison between these different methods. By the way, I should note that this comparison is coming from the Singularity paper, so you should see that they have all yeses, because it's a bit subjective, I would say. But we can see the advantages of Singularity compared to Docker. The first one is this root access in Docker versus user-level access on Singularity. This is the main problem with Docker that cannot be used in HPC because of the security risk. A user can have the root privileges, and it can harm, since it can also access the host file system, it can create a security risk. So there are other differences between these different technologies. So Singularity becomes very useful because it can work with any scheduler, while Shifter works right now only on the Slurm scheduler. It also allows building a recipe based on just Singularity's definitions, while the others rely on Docker images. Singularity can also use Docker images, but you can also build images based on Singularity recipe files. The main question that is asked about containers is how much overhead I am paying to use these tools. So there have been various studies, and most of them actually came alive just last year. And I will just show them to you, and you will see that the overhead is really minimal. So here, a group has different applications which have different type of memory or CPU requirements or network requirements. And for all of them, we see that Singularity is very close to native runtime. This is another one where we have now more point-to-point communications, and it is more data-intensive workload. And the overhead, in general, they found out is less than 8% for CPU-intensive, memory-intensive, network-intensive, or I/O-intensive applications. Obviously, this may change based on your application and based on the environment you are running in. But I will show you some other results. This is from another study. And what they see is actually they also report less than 1% overhead. Another study basically look at the startup time using a container, using a Singularity or a Docker. And you see that the startup time that you have to pay, independent of what type of application you have, is about less than 100 milliseconds. So this is also very encouraging in terms of you can even do high throughput calculations on using containers. The penalty you pay is really minimal. And this paper actually has some interesting results which are a bit hard to believe. They have been showing that they have seen better performance within the container compared to without the container. And their explanation for that was a Singularity container is not making any emulation for the full hardware system, and you are using only a small amount of the Linux kernel namespace. And for the single metadata lookup can be faster. We are seeing some performance improvement. So I'm not sure how much to believe in that one, but we have also, I'm going to show other results where Singularity container can be faster than native in some certain applications. So let's put it this. And here are the latest results. These are coming from a summer intern, Spencer Williams, and his supervisor, Taylor. They have investigated basically the overhead for Singularity on Theta, and they have run these calculations on 128 nodes, 256 nodes, and 512 nodes. And what they do is they are looking at the bandwidth for different message sizes, and they use Ohio State University micro benchmark set. And for each data point, they use 1,000 runs, and you are seeing here the relative bandwidth in container and out of the container. And you see here, if you are using 128 or 256 nodes, the penalty is about 10%. And it is getting smaller as the message size increases. I guess this is because since the message size is large, the overhead you pay becomes less. With 512 node, the penalty is more. But I should also note here that we have very large variations here. And if you have attended yesterday's talk, we have seen that various reasons affects the runtime on Theta, like the network congestion or other stuff that can result in these variations. So this needs to be also taken account. So this is another benchmark, which is looking up an interesting case where they have created n files for n MPI ranks. And in these scripts, they have two scripts. One is creating the files, and another script is checking if these files exist or not. And what they have seen is that they get almost 6x speed up within containers. The reason for that is caching in Singularity images. So once you run the container, it caches the files, and once it's checking, it's going to be much faster when you repeat those checks. So if you have an application where you have lots of files and you have to open these files, containers can give you an advantage. This is something also reported with Shifter. They have seen this when they do Python applications, when they are importing modules. So importing modules also become faster within a container. So there are some applications that can help the performance in containers too. So okay, if you are convinced, let's talk about how we can start using containers if you have not been using it. There are various resources I put here. Obviously, the basic one is looking at official Singularity documentation. And Taylor also put a very nice documentation on how to use Singularity on Theta. You can follow this link. There are similar tutorials from other HPC centers that I put here. And you can look at Singularity repo on GitHub and check the issues if you have any problems. Another place to ask about this is they have a very vivid Slack channel. I forgot to put the address here, but they have a Slack channel. If you search on Google, you will find the Slack channel. And if you just register there, you can ask your questions directly there as well. And to find images, the best place is going to the Singularity registry. They have a hub like Docker Hub. And you can reuse recipes in Singularity registry, or you can use those the recipes on Docker registry as well. If you have, and I guess many of you have, a sudo access on a machine, it can be your laptop, or it can be even a Raspberry Pi machine. What you need to do is you just install Singularity and start building images there. The next thing you will do is you transfer those images to Theta. This is, I think, this can be the most productive way of working with containers, because if you have the sudo access, you can build it from the recipe, and then you can test it, and then use it in other places as well. If you don't have any place that you can run as root, or if you don't want to install Singularity, the other option is you connect your GitHub account to the Singularity Hub account. Actually, to register to Singularity Hub, you need to have a GitHub account. And you need to link your account, and then you link the repos that you want to use as Singularity images, which contains the Singularity recipe files. Then Singularity Hub will automatically build your recipe files. So you don't need to build those files yourself. But there is another catch here. The Singularity builds on the cloud are restrictive builds. So they have, due to security reasons, their builds are very sanitized. So they don't allow any type of builds. So for example, if your configure file has some, checking some executables, running some executable, and in many configure stage, you run some executable. So they may not allow in that, and you may get an error on such builds. Another option, if you don't want to deal with recipe files, is just search the Singularity Hub and look at the images. Maybe the application that you want has already an image, and this will be very helpful. Okay, I would like to give another sort of warning here. The way containers and images are described within the Singularity community or Singularity documentation and Docker is different. And I'm not sure why it is like that, but I think Docker manual has a much nicer definition about this. An image is basically an executable package that includes everything. That's the file that includes everything. And this is what you build when you use a recipe file. You build an image. A container is basically the runtime that you run your image. Just an instance, that instance is called a container. So you can run 10 containers using a single image, for example, on the same host. But Singularity manual talks about building a container from a recipe and refers to image only when they refer to the file. So this confused me, so I'm just warning you about this. So there is this difference in the Singularity manual. They talk about, when they mention building a container, what they are actually referring to is building an image within Docker's sense. So, okay, what are the commands that we can use on Singularity? Basically, we can use the build tool to build either from a recipe or to convert from existing images or to convert images. Another option is to run a Bourne shell within a container, which is a very useful feature. You don't, after you build, you check with shell if you have done everything correctly or not, and work in your environment. Exec is to basically specifically run a certain command. And run is launching the run script within your Singularity recipe, which I will talk later. And Singularity has a nice feature. I think you don't have this in Docker. You can have different apps within a single recipe file. This will allow a single image to be used for different applications using the same environment. There's another command pull, but I don't see much use of it. I mean, if you are building it, you don't need to pull separately. When you build, it does the additional step of converting the image to the version that you are using. But build should be fine for you. So how do we make the build, and what are the options Singularity provides? So the first thing, which is the easiest one, which doesn't require the sudo access, is building an image based on the images on the cloud, on the registry. Either you can use a Singularity Hub or the Docker Hub. And this XXX corresponds to the username, and YY is the application name, and Z is the version of it. And the options allows you to build an image either in, by default, the squash fs compressed format, which is read-only, or you can create writable images in X3 format. This requires the sudo access. Or you can create a sandbox. Sandbox is basically a directory. Instead of creating a single file, you are creating a directory, and everything is inside that directory. And you can make that you can write into that sandbox, but to make what you write persistent, you need to add this dash dash writable, and you need to run it with sudo. So these are showing you all the different options with Singularity. If you are on Theta, basically you cannot do the things that require the sudo access. So we cannot use a writable image, and we cannot build from the recipe. But we can still use what we have on the Singularity hub, or we can copy the image that we built to Singularity, and we run basically Singularity using that image. A good feature of Singularity is binding volumes. So this is done with this -B command. And the first one is the location in the host path. The second one is the container path. And the last one is basically the option for read-only or read and write. By default, it's read and write. And this directory should not exist on your container, may not exist on your container. Depending on the configuration of the Singularity on your cluster, let's say on Theta, on Theta they allow overlays. That means this directory, if it doesn't exist, created automatically. On some configurations, they don't allow overlay. So if you don't have a directory named data in this path, then it will give it doesn't give an error, but it doesn't create it. So just another warning. So far I explained things look simple, but when we try to run MPI applications, things become a little bit difficult. In principle, it should not, but since we are using Cray MPich, and this is not available publicly, we have to build our image in a certain way. So this is what I'm going to explain next. So what we need to do is we need to build our image externally and then copy it. Either we have a recipe file that obeys a certain structure and we upload it onto the cloud, or we copy our image that we built and on Theta. And the next step is going to be basically changing the dynamic linking of your application to Cray MPich. So now that's what I'm going to explain. So this is from Taylor's guide. You can see it on the ALCF web page as well. So this is what you see here is a recipe file. And this recipe file has a certain structure that allows us to run this image on on Theta with MPI. So what are those? So first part is basically the stuff that you need to copy files. Note that this file should exist on the directory that you are in, or if you are on GitHub, this should be on the same repository as the Singularity recipe file. This file and this file should be on the same directory or on the same repo. And you need to basically do all these copies in the setup section. And note that we start with Singularity rootfs, because at this stage, during the setup phase, the file system is still on the host file system. So you need to specify this. But at the end, this will reside, this directory will be on /myapp. There will be no prepending after it is built. So after this stage, this is the post stage where you do all your installations. The catch here about mpich is what we need to do is we need to first disable the RPath, and we configure with this. And we need to export the path and add the library path, and then we build our application, which is a simple file code that calculates pi using mpich. So this is another flag we need. So these two flags, this flag we need in the configuration stage, and this flag we need in the build stage. So this allows our application to be able to run with MPI on Theta. But there are other things that we need to do. And the last thing is basically specify what is going to be run when you say Singularity run my image. We are specifying which executable is going to be run. Okay, so here I have shown you an application where we build mpich, and then we build our application. But we can make our life easier if we basically use an image which has already mpich built in this specific fashion. So if we have such an image, one is here, and we have other ones. So basically, you start from that image. Previously, if you look here, we start from a CentOS image. So this is basically a very clean CentOS image. It doesn't contain anything, and we install GCC, and we get all the tools that we want. But if we start from an mpich installed image, our life is much easier. We just need to build our application. Here, I choose an application as Keceli, which is a mathematical library that I use a lot, and there are many users of it. And the installation can be quite difficult and takes time. So having an image is very useful. So what I do is here, basically the same steps I do if I was going to build this on any other place. So I do a git clone, and then the thing you need to do is you have to specify the path and the LD library path again, because it needs to read this. And all the steps are basically the same steps that you would do in a Keceli installation. But there is another catch here. When you try to upload this recipe and run it on Singularity Hub cloud, you get an error. The error is coming from this problem that I mentioned. In the configure stage, there are some binary runs that is not allowed. There is a way to avoid it, but right now this recipe doesn't contain it. So it doesn't exist on the Singularity Hub. But what you can do is you just build this on your laptop and then copy that image to Theta. So this is a simple workflow that you can make things work. So basically, if your image is large, the best thing is use Globus for the file transfer instead of SCP. But SCP is also fine if you are less than 100 gigabyte. You can follow this. And the other thing I mentioned, I guess I don't need to go through this. You can create the GitHub account if you don't have, and then link your Singularity Hub account with the GitHub. And you select here, basically, it sees all of your repositories, and you basically switch on whatever repo that you want to enable. Those repos should contain the Singularity recipe files named Singularity. And then it will automatically start. If it doesn't start, just click this refresh button. Starts building your image. And you will see if there's an error, you will see the error message. If it is pending, you will also see. And if it is complete, you will see. So after we did this step and copy our image to Theta, what's the next step? We can either do this by building our image from Singularity Hub or copying our image from our laptop. So both are fine. The next step is submitting the job. And to submit this job, we need to do some steps in our submit file. Everything is same on top, but here we need to make a swap from the Intel work environment to GNU work environment, because we have been using GCC. Another thing we need to do is we need Cray's application binary independent MPI build. This is also required. And the next steps are basically putting all the libraries in the right place and then passing it to Singularity environment. You do this by basically prepending your environment variable with Singularity env, and then Singularity takes all of these Singularity env prepended environment variables and uses in the image. So these are the steps you need to do in the submit file. And another important step is you need to bind the volumes, because this LD library path is looking into opt Cray, which doesn't exist on your host or on your container. So we need to bind our directories existing on Theta to our image. To do that, we use this -b flag, and we bind the path in the host to the container, which doesn't exist now, but since Theta allows layers, it is created automatically, and it binds it. Same here. And then we just run our image. And we note that the app run is outside. The way MPI run or app run works is always outside of Singularity. Singularity handles the rest of the MPI communication. I mean, you don't need to do it inside the container. It's always outside. In summary, what I tried to show you was containers can be helpful for portability. It can be, it can help you to create reproducible workflows, and it can help you to have faster development cycles. It has minimal overhead, but you should also be careful that there might be additional performance penalties because, for example, we were using GCC. If we were using Intel compiler, maybe we would gain some additional 10-20%. We have fat images, which may not fit into the cache, and this may decrease the performance a little bit as well. And the optimization, like AVX512, we don't have it here. This might also create, but these things can be worked out, actually, if you put more effort into your recipe. And I believe that if there are more HPC interest in containers, this technology evolves very fast. I actually feel like when I started using Python in HPC environment like 4 years ago, it is not recommended for many people that they say don't use it. But now many people are using it and it is evolving fastly. So I feel the same here, and Singularity and other HPC containers will evolve very fast, and we will have good solutions from also maybe from Cray and Intel helping us to run these on HPC environment flawlessly. So here are the resources that I mentioned, and there are several papers published just last year. I put the references as well. And I will be glad if you can complete this poll. And if you have any questions, I will be glad to answer too.
I want to port an application between ALCF and NERSC. Do Singularity and Shifter talk to each other? Are they compatible?
So both of them can use Docker images, but both of them has the special steps that I mentioned here. So in your submission script, you have to have the special commands that you have. But I have never tried this. Ideally, you can use the same Docker image in both of them, in Shifter and on Singularity on Theta. But I have never tested it. So,
can I ask one other unrelated question? Can you comment on the relationship between containers and package managers like SPAC, for example? Because, I mean, it seems like you could build an application with a SPAC recipe, or you can build an application through a container. Are those two things disjoint, or can you use a SPAC recipe inside of a container recipe? How should I think about those two technologies?
Both are trying to answer the same problem. Both are trying to make the life easier for compilation. But the approach taken is different. In one of them, basically, in package management side, is very low level. So you are basically using all the features in your environment, and you try to optimize your build. Here, we are basically trying to create a image that can work everywhere. So we are sacrificing from that optimization here. So there is that difference. I would say the package managers are lower level and could give you more optimum binaries at the end. Here, you will have more portability, but less optimization.
How to build a Singularity container that sort of,
Yeah, that's a very good question. So the key here is to do dynamic linking. So once you do dynamic linking, at the end, you can switch the linked library at the submission stage. So if you do that, you can use the optimum libraries built for that environment. The question is how is the relation between the workflow managers like Balsam and Singularity? So is there some, can we use them together on Theta, right? I think we haven't tried that, but we have talked about it. it is possible and could be a very useful solution. We can combine these two features because sometimes porting the application is difficult, but then you want to use that application within a complicated workflow. And you may not want to put everything in the container, but you may want to, for example, you have a certain application from quantum chemistry, let's say a software package, NWChem. It's hard to install. And then you have a workflow on top of NWChem. Instead of compiling NWChem on Theta, you can use the Singularity image of NWChem and run the Singularity image of NWChem with Balsam for your workflow. So this can work, but we have not done that yet.
I just wanted to jump in and say we have done some, for the LSST ADSP, we have used Singularity as an application in Balsam.
Great. Yeah.
It works in that way. Is if you're using like that Singularity exec mode, it's just another app to run, like exactly like you described.
Yes, that's a good question. But what you can do is, even when you are installing on your laptop, you can still put the flag that gives you a FAT binary that can work with AVX512, for example. Intel provides, I think, that flag for us. So even on your laptop, or what we are doing is actually, we are building the application. I mean, the place where we build the image is not important. It can be your laptop or any other place. But the image is based on, let's say, Ubuntu. And the flags that we use in the compiler didn't contain AVX512. Then obviously you cannot make use of it. But we can put those flags and make our recipe more complicated, but create fatter binaries, fatter images, but make advantage of the vectorization. So it's possible.
Another question. You emphasized app option, I mean command.
Yes.
I could never understand why it is there. I mean, exec takes care of running anything.
You are right, but that's just another simplification. Yeah, exec is there. That's right. And well, let me give a point on the reason. You can find out which applications are loaded on a specific recipe, on a specific image. There's a command for that. You type Singularity apps and then the image name, and it lists you all the images that you have. But otherwise, you need to look at the recipe to find out what you can run or get into the shell mode and see what is available there. Apps help you what kind of applications are there. So it's another helper. Yes.
Do you have any variants or pointers for running profiling applications running inside of a container?
Not me. I have never run a profiling inside. Yeah.